to everybody. Welcome to the beginning of the academic year. Very happy that you all came. We will celebrate the beginning of the academic year next week. So I apologize for those who will not be here in 1 week. And now I would like to give the floor to Art and we will present the speaker.
Okay, welcome everyone. Today's speaker is Jove Campabadal from University of Barcelona. She will talk about boundaries of Baker domains of entire functions. Joint work with Fagella.
So thank you for inviting me to the seminar. We'll start. So in this talk, we let F be a transcendental interfunction. And as usual, we consider the Fatou set and the Julia set. So the Fatou set is where the dynamics are stable, and the Julia set is where the dynamics are chaotic. And our goal in general, given an entire function, is to understand how F acts in the Julia set. Basically, because in the Fatou set is everything very well understood, so we already know, and the goal is to understand how F acts on the Julia set. But this may be difficult, and one thing that we can do to turn this question to an easy question is to consider U to be a periodic Fatou component. By Fatou component, we mean a connected component of the Fatou set, and then its boundary is in the Julia set, and it's forward invariant. So we can consider F from the boundary of U to the boundary of U. Well, sorry, I put periodic, but in fact, we will assume invariant. So if it's not periodic and if it's of period larger than 1, we replace F by an iterate of F, and everything works the same. So we have our map F from the boundary of U to the boundary of U, and so instead of considering the whole map in the Julia set, which may be very difficult, we restrict to a smaller subset of the Julia set, and we hope that this will be easier. And in fact, we may think that this is going to be easier because we can deduce some things from the internal behavior on the Fatou component, which is on the Fatou set, and that we know very well what's going on. So in this talk, we are going to try to understand this map for a precise type of Fatou component, which are Baker domains. So let us start. So let U be an invariant Fatou component. Then, by a theorem by Baker, U is simply connected. This means, in particular, that one can use the Riemann map to conjugate the map F to a self-map of the unities. So if we let phi to be a Riemann map, then G is a self-map of the unities, and well, we can use this map G to understand the dynamics in U. So the dynamics in U are, of course, related to the dynamics of in U are related to the dynamics of G in D. So this is of course true because phi is a conjugacy, but what we want to explore in this talk is if there's some relation with the dynamics of F on the boundary of U with the dynamics of G on the unit set. And this is not that clear because phi may not extend continuously to the boundary, G may not extend continuously to the boundary, so I don't know, this diagram may not make sense, and well, we will see during the talk. But first, let us start with the dynamics inside the F2 component and inside the unit disk, which is easier. So the dynamics of G in the unit disk. So the advantage of considering this map in the unit disk in front of considering the map F in the F2 component is that there are a lot of results concerning maps in the unit disk that we can apply to understand then F in U. So the first well-known result about iteration of maps in the unit disk is the so-called Jove theorem. That says that if we have a map G from the unit disk to itself, then two things may happen. Either G is conjugate to a rotation, to a rigid rotation, so or there exists a point either inside the disk or in the boundary such that all orbits converge to this point. And this special point is the Jove point. And what is important about this theorem is that we do not assume anything about the map on the boundary. So the map may not extend continuously or anything to the unit circle, but still there exists a point towards which all orbits converge, and this point may be in the unit circle. So basically, this is telling us that we have three possibilities. So in the case A, there may exist a point around which all orbits turn. Or in case B, there may exist a point either inside the disk or in the boundary towards which all orbits go. So in the case that the point is in the Jove point is inside the unit disk, then applying results like Butker's coordinates or Koenig's coordinates, one can linearize the map around a neighborhood of this point. So there exists a neighborhood of the Jove point in which we have a well-known normal form. So here there exists a normal form on this part. But in the case where the Jove point is in the boundary, a priori we don't know that the map extends in a neighborhood of the Jove point. So a priori we don't know if there exists a normal form around this point. But the answer is that yes, more or less there exists a normal form. So let me explain. So here, if the Jove point is here, one has to be careful because maybe G of P is not defined. because as I said, we are considering general maps defined on the unit T, so we are not assuming any kind of extension to the boundary. It may happen that the point, the Jove point is one of these points for which the map doesn't extend. However, P is always fixed in the sense of real limits. So G star of P equals P. So by G star we denote the real limit, which is the limit of Rp when R tends to 1. So if we take the radius going to P, the image of this curve is going to be another curve, also laminar P. And about trying to find a normal form or coordinates around P, this is what it's called Cohen's theorem. So asking if there exists a normal form around P is the question of this existence of a normal form is answered by what is known of Cohen's theorem. And let me try to give an idea of this beautiful theorem. So first, instead of assuming the difficult case where the image at P is not defined, let us assume that G extends analytically around P, and let us see what we can do. So assume G extends analytically and then then P is a fixed point. So we knew that it was fixed in the sense of real limits. If we have that the map extends around P, it should be fixed. And it should be attracting, or at least weakly attracting, because we know that all points in the unit disk converge to P. So we have that the derivative of G at P, well, it should be real because the map preserves the unit circle. Well, sorry, here I should say more maybe. Well, we will assume that G is a finite Blaschke product, which is the cases we are going to consider next. Then we have that the derivative should be real because it should preserve the unit circle. So we cannot have rotation around this point, and then it is either attracting or parabolic. So one option is that our the Jove point P acts as an attracting fixed point, so that the derivative is smaller than 1, or in the case that it is parabolic, we only have two options, because since G maps the disk inside the disk, and then by reflection the exterior to the exterior and the unit circle to the unit circle, we at most can have two petals. So one option is that we have two petals, so that points inside converge through this petal to the Jove point, and points outside converge through this petal towards the Jove point, and points in the unit circle are repelled. Or the other option is that we only have one petal which is symmetric through the unit circle, and here points are repelled, but here points are attracted. And we refer as this case, sorry, this case is the hyperbolic case. and this case is a doubly parabolic, and this case is a simply parabolic. And in these two cases we have that the derivative is 1. So these are the three options that we can have when we know that the map extends, that we have a finite Gaussian product. But what Cohen's theorem tells is that this is in fact true always. So even if we don't assume any kind of extension around the Jove point, this is happening, of course, in a weaker sense. So what Cohen's theorem says is that this happens in a one-sided neighborhood of the Jove point. So instead of having this linearization around the Jove point, we have a neighborhood in which we have these coordinates. Here we have, well, one of the petals acts as this neighborhood, and here we have half of a petal.
Do you assume finiteness?
No.
Degree here?
No. Cohen's theorem holds in general. We don't assume anything. So for any, sorry, here I should write holomorphic. So for any map from this to itself holomorphic, Cohen's theorem holds.
You assume it is inner function.
No, from now this is general. Any self-map of the unit disk satisfies this.
No, but in Dynamical.
No, also the Jove theorem is general for any self-map of the unit
By
disk.
inner I mean if the sequence of points tends to the boundary, then the sequence of images tends to the boundary. You don't need this.
No, you don't need this for the Jove.
But when you use it for dynamics, you have this.
Yes, and we will see it now that we have this. But these two theorems for self-maps of the unit disk are true in more generality. So let us see how these things about self-maps of the unit disk transfer to Fatu components. So since we have a conjugacy given by the Riemann map between F in U and a self-map of the unit disk, we have three possibilities that we will see they are formal. We said that the first option is that the map is a rotation. Then we have what it's called a Siegel disk. So a Fatu component in which the map is conjugate to a rotation, we call it a Siegel disk. Another option is that we have that the Jove point is inside the unit disk, then we have an attracting base. So a Fatu component for which there exists a point inside, a fixed point inside, towards which points converge. And if the Jove point is in the boundary, then we have to distinguish two cases, the case of a parabolic basin and a Baker domain. So parabolic basins are Fatu components for which there exists a point in the boundary and orbits converge to this point. But this point is a fixed point for the function. So it's a point in the complex plane and the function is defined at this point and this point is fixed. The alternative, a Baker domain, is a Fatu component for which orbits also converge to the boundary, but now the point of convergence is infinity. And since we are assuming that our map is transcendental entire, the map is not defined at infinity, so we cannot extend the map to this point. Then, regarding what we said about this classification of self-maps of the unit disk in these three types, Well, parabolic basins are always doubly parabolic, so the associated map G for parabolic basins is always doubly parabolic. And one can see this using Fatou's coordinates. So Fatou's coordinates give you the existence of a petal here, which is the same petal that you see for the map in the unit disk. But for Baker domains, we have that the three types are possible. So we can have Baker domains of hyperbolic type, of doubly parabolic type, and of simply parabolic type. So for the ones of you that are not used to work with Baker domains, it can be easy to think that, well, a Baker domain is a parabolic basin at infinity. Because, well, there's a point which is infinity, but points converge to it, so we can think as a parabolic basin. But no, this is a very big mistake, because the dynamics inside may be very different for the ones of a parabolic basin. So Baker domains, which are of doubly parabolic type, they are similar to parabolic basins because we have the same internal dynamics, but hyperbolic and simply parabolic Baker domains, they are really different from parabolic basins. So I think it's not a good idea to think that a Baker domain is a parabolic basin at infinity. So this is what I wanted to say concerning internal dynamics, but let us turn now to study the dynamics on the boundary, which is more interesting. So we have this diagram. And well, we may like to extend this diagram to the boundary, but well, this may have some problems. But the first observation that Felix already said is that since F maps the boundary to the boundary, we should expect somehow that G maps the boundary to the boundary. Of course, this, for the moment I put quotation marks because we don't know if G extends to the boundary. So for the moment, let me write it like this. But, well, in any case, we should expect something like this because F maps the boundary to the boundary, so it doesn't make sense that our G doesn't reflect this behavior that we have for G. And let us start with the easy case. So if F has finite degree in U, and G is a finite Glasgow product. A finite Glasgow product at the end is a rational map. So we have that G, well, G in fact is a map from the Riemann sphere to the Riemann sphere, and G of the unit circle is the unit circle. So G is well defined in the unit circle and maps the unit circle to itself. So in this case, it makes sense to study the dynamics of this map and then try to push it forward somehow to the boundary dynamics of F. But since we are considering transcendental interfunctions, we may not be that lucky, and it may happen that F has an infinite degree. Well, in this case, if f has infinite degree, then G has infinite degree. And this already implies that, that at least there exists a point in the unit circle for which the map doesn't extend continuously. This point is a singularity, but it may happen that all points in the unit circle are singularities. So we cannot assume any type of extension to the boundary. So we may have singularities in the unit circle, and so in this case we cannot expect a well-defined map like in the case of finite degree, but still we can work with radial limits and have kind of a measurable extension. So instead of working with the whole image of G at a point in the unit circle, we will work with radial limits. So for a point in the unit circle, the radial limit is defined, well, as the limit along the radius. So, if this is the unit ds, we pick any point, we consider the radius, we consider its image, and we see where this happened to land. So it may happen that this limit doesn't exist, but it exists for almost every point. And this allows us to consider a measured theoretical dynamical system in the boundary. And this will be enough for the things we want to do. So we have G star from the unit circle to the unit circle defined lambda almost everywhere. So lambda is the definition. Okay, so we can consider this dynamical system and study its ergodic properties. So this is one question we can try to answer for this dynamical system. But there's another question that makes sense that we may like to study, which is do orbits in the boundary also converge to the Jove point? So we said that that all points inside converge to this Jove point. So what happens in the boundary? Are orbits also converging to the Jove point? They are not. Some yes and some no. So this is a question that may be interesting to ask. And we will denote by the Jove set the set of points in the unit circle which converge to the Jove point. And these questions that I write are answered. So case that we have extension around the Jove point, then the boundary map is also recurrent, and then the Lebesgue measure of the Jove set is 0. And on the other hand, if G is hyperbolic or simply parabolic, then G star is non-ergodic and non-recurrent. And the Jove set has full measure. So we have kind of a dichotomy. Either no one goes to the Jove point and the map is ergodic and recurrent, or the map is non-ergodic and non-recurrent and all points go to the Jove point. And well, this theorem of course is true, well, it's in this sentence, when the Jove point is a singularity, but if the Jove point is not a singularity, I want to convince you that this is what you should expect from looking at what's going on around the Jove point. So that this is somehow what you should expect. Why? Because if it's doubly parabolic, it is repelling the Jove point as a fixed point, is repelling on both sides of it. So you should not expect orbits to converge. So they cannot converge approaching this point. Instead, for hyperbolic or simply parabolic inner functions, the Jove point attracts orbit. So this point is attracting as a fixed point, so in particular attract points in the unit circle, and for simply parabolic attracts on one side of it. So you should expect that there are points that converge to this point. Okay, good.
I think one should comment, maybe you will comment it later, is I look from the point of view of the invariant measure. And if this fixed point is in the disk, then a harmonic measure viewed from this point is invariant.
Yes.
And if it is, as you discussed it in the boundary, then it's in one of these cases we have a situation similar to parabolic,
Yes.
with invariant measure equivalent to Lebesgue, which is infinite.
Yes.
And then we have this problem for infinite measures, conservative or non-conservative.
Yes, so if you consider these two cases where the derivative is here I wrote the derivative, but this is true for angular derivative if you have that the point is a singularity. It's also true putting the angular derivative. Well, in any case, for the doubly parabolic or the simply parabolic case, if instead of looking it at the unit disk, so this is a map from the unit disk to itself, instead of considering the unit disk, one can consider it in the upper half plane, and then one can put the parabolic point at infinity. Then for these two cases, it's true that the Lebesgue measure is invariant. But in this talk, we are not going to. So this is very interesting, but we are not going to do this today. But it's true that it's very interesting. So okay. Well, what I was saying, that this theorem of Aronson, Riemann, and Fagella, Karpinska more or less answers our questions for inner functions. And then the question is how we apply this to boundaries of two components. So the first, the first idea is that we can consider also the radial limits for the Riemann map, and then we have that the diagram, the following diagram, commutes almost everywhere. So we denote by phi star the radial limits for the Riemann map. Then this diagram commutes almost everywhere. question that we may address is the one of the ergodic properties of F in the boundary of U. So the theorem says that if G star is ergodic or recurrent with respect to the Lebesgue measure, then F in the boundary of U is also ergodic or recurrent with respect to harmonic measure. So before going on, let me comment that we are considering harmonic measure and we don't care about the base point. So harmonic measure is defined with some base point inside the domain, but since we are only interested in ergodicity and recurrence, and these properties are defined up to a set of zero measures, and all harmonic measures have the same sets of zero measure, we can write it in general without specifying the fixed point.
We don't care about invariance.
No. And this and well and this theorem is in principle not obvious because phi star even although phi is bijective inside the unities, it may not be bijective in the boundary. So one has to prove something. So the first observation is that for entire functions, phi is an isomorphism. So this is due to Barman. Well, neglecting the points that are sent to infinity, there may be plenty of points that are sent to infinity. We don't care about them. We only care about the points that are sent to the finite boundary. This is an isometry, and then this means that this gives that the ergodic properties of G should be the same as the ergodic properties of F because this is an isomorphism. But this correspondence of ergodic properties is true more in general, for instance, when F is meromorphic, and in the case where F is meromorphic, one can rely in some properties of the Riemann map to prove this. So, more in general, for instance, if F is meromorphic, one can still prove the theorem, but using the following fact about Riemann maps. So if phi from the disk to U is a Riemann map, any Riemann map, so not assuming that U's have two components, so in general for Riemann maps, there exist countably many points which have at least, at most, three preimages. And this is telling us that in a set of full measure, the Riemann map is not that wide, so at most is 2 to 1. And knowing that at most is 2 to 1 is enough to prove this correspondence between the two things. Okay, so the first question that we ask about the ergodic properties, more or less, is well understood. And now let us see what we can say about convergence to the Jove point. So U to be a Baker domain. This means that points inside the Baker domain converge to infinity. So in this setting, it's well, logic to define the Dynamical set in the boundary of U as the set of points in the boundary of U which converge to infinity and their iteration. So as we did for the map for the inner function in the unit circle, we consider the set of points which converge to the Dynamical point. Now, the point in the Fatu component which plays the role of the Dynamical point is infinity because all orbits inside converge to infinity. Well, let us see if there are points that converge to infinity, if how many, or what we can say. This set was studied by Riemann and Staller and by Baranski, Fagella, and Karpinska. And their theorem, putting the two things together, says that if P, so we have, well, our favorite diagram, this is G, and let P be the Dynamical point of G. In this setting, if P is not a singularity, then it happens what we should expect, that the things that we knew for the inner function also holds for the Baker domain. So if G is doubly parabolic, then the harmonic measure of the Dynamical set is 0, and if G is hyperbolic or simply parabolic, the set of points that converge to infinity have full measure. Okay, well, you may complain and say that trying to see that this hypothesis is satisfied, it may not be the easiest thing to do because given a map F, you should be able to compute explicitly the map G, and this may be complicated, but this is true if finite degree, because as we said, if we have finite degree, the associated inner function is a Blaschke product extends to all points, so in particular for the Dynamical point. And also it's easy to prove that if we have singular values compactly contained in U, also happen. So this hypothesis may not be easy to know if it's true or not, but in many cases we know that this applies. Which is the difficulty of this theorem? So why we have to assume that P is not a singularity, which we didn't assume here? Well, because phi may be very discontinuous in the boundary, well, in fact always is very discontinuous to the boundary. So having points that converge to the Dynamical point in the unit circle, since phi is very discontinuous, doesn't translate to having points that converge to the Dynamical point in the dynamical plane. So this is really difficult. And one other thing that one can observe looking at this theorem is that it only gives information about the measure of these sets, but for instance, this doesn't answer the question if in the doubly parabolic case there exists any escaping point, or on the other hand, in the hyperbolic or the simply parabolic case, if all points are really converging to infinity, or if there are other points doing other things, or well, we don't know. And we want to, well, one of the things that we are going to do next is try to understand if there are points doing other things. But before continuing, let me say that maybe this the Jove set is not the best thing we can use to understand when points converge to infinity or when not. And now I'm going to explain. So we have here the unit disk and the map G, and then take a Riemann map. In general, a Baker domain has several accesses to infinity, so several ways of going to infinity. And points inside, although all of them converge to infinity, they are converging through the same axis. So it's not that one point inside goes like this to infinity and the other way, but there exists an axis to infinity, and all points converge to infinity going through this axis. Well, this is exactly what we see in the unit disk. If points would converge, one going to one side and one going to the other, in the unit disk we would have seen points going here and points going here, and we are not seeing that. In the unit disk we have one point, the Jove point, and all points converge to here. This means that there exists one axis and all points converge to infinity through the same axis. And this is what we call dynamical axis. So maybe the question that we have to ask is not if there exist points in the boundary of the Baker domain that converge to infinity, but if there exist points in the boundary of the Baker domain that converge to infinity some way, somehow, through this dynamical axis. And this it's going to be our Carathéodory set, because these are going to be the points that converge to the Jove point in the sense of Carathéodory. And now I'm going to explain. Well, so, and this means through the dynamical axis. So points that are truly converging to the Jove point when sit in the unit disk. And now let me explain this. So the notion of, well, Carathéodory give a compactification of any simply connected domain using the theory of prime ends that now, well, I'm going to try to explain what we need here. So now, let us see infinity is a finite point in the plane, and if we have several axes to infinity, well, this should look like this. So we have several ways of going to infinity. But when we look at this, at the unit circle, at the unit disk, these pieces should look as disjoint neighborhoods of the boundary. So even though...
Sorry, the question?
Yes.
Are there only finitely many axes always?
No, in general there are infinite.
Can it be continuum?
No. No. I think so.
You can continue on domain. Not enough space.
Yes.
So, even though when we look at our domain from the outside, we see that all these pieces are going to infinity. If you are inside the domain, you are not seeing that all these paths are going to the same place. And this is more or less well, what the theory of Carathéodory tried to explain for a general domain, not necessarily a Cato component. So, in order to know towards which axis you go, one can use what are called crosscuts. So, a crosscut is nothing less than nothing more than a curve cutting the unit circle at 2 points. But this is telling us if we are conversing through the image of points in this arc by the Riemann map. So the difference between conversing to one axis or the other is that we eventually enter this crosscut neighborhood or we eventually enter another crosscut neighborhood. These crosscuts kind of split the boundary and give you the different possibilities of the different axes. Okay, so maybe here. The formal definition for the Carathéodory set would be the set of points in the boundary such that for any crosscut neighborhood at the Dynamical point N from some moment on we are in the image of this neighborhood. So if we look at the drawing again, we have our Dynamical point. We take a crosscut at the Dynamical point. This is the crosscut neighborhood, and this goes somewhere, I don't know, here. For points in the inside, since they should converge to the Dynamical point, eventually they enter this crosscut neighborhood. So they do the same here. They eventually enter the path compression. So points that in the boundary that converge to infinity through this dynamical axis should enter the closure of this region here. This means that these points are not converging to infinity through the other two axes. But this should hold for any crosscut neighborhood. So take a crosscut neighborhood smaller, and then you will get a crosscut neighborhood smaller, and this kind of deletes this axis. So when you take all the collection of crosscut neighborhoods bringing to the point, you are left with the dynamical axis. So points in the boundary that are on all these crosscut neighborhoods are going to be the points that are in the dynamical axis, and we call these points that are in the Carathéodory set. So as we will see, so in a moment we are going to see examples, and we are going to see that in some cases there are a lot of points in the boundary converging to infinity, but they are not converging through the dynamical axis. So in fact, even they are converging to infinity, they are not doing the same as points in the inside. This is why we define the Carathéodory set, because it's the notion of points in the boundary that do the same than with points in the inside. The Jove set, although it seems to be this notion of points that do the same points in the inside, as we will see, there may be a lot of points converging to infinity, but they do several different things. And well, maybe it's a good moment now to see the examples. Artem, can you help me? Or you can move on. Okay. No, yeah, I can do with my hands. This is the drawing of the function z plus e to the minus z, which has a doubly parabolic Baker domain of degree 2. So here in orange, there's this Baker domain, and well, maybe it's not really visible, but in red, it should be the points that escape to infinity, which are in the boundary.
Do you want us to change the light?
No, well, if you more or less can imagine the red things, I think it's okay.
You can turn off the light. Yeah.
So, the boundary of this Baker domain, it's known that it consists of uncountably many curves. In fact, more or less we can see these curves. And all these curves are made of points that escape to infinity. But we said, well, now you cannot see because it's below the screen, that for a doubly parabolic Baker domain, points that escape to infinity have zero measure. So even though the boundary is made out of curves that escape to infinity, of points that escape to infinity, maybe not the endpoint, but the rest of the curve, yes, these have zero measure. And now we will try to see this with the eyes of this character-theory convergence that I explained. So for points in the Baker domain, orbits converge to infinity going to the right. And for points in these curves, points converge to infinity going to the left. So in some sense, we are seeing this here, this phenomenon that there are points in the boundary that escape. There are plenty of points in the boundary that escape because the boundary is made out of curves of escaping points, but this escaping is made in a different direction. So it's clear that the axis to infinity, the dynamical axis is the axis to the right, but points that escape to infinity in the boundary do different things. And if we try to look at this from the perspective of the inner function, it's easy to see. So, as I said, this Baker domain has degree 2. Things are even better because we know the explicit example for the inner function, but even if we didn't know this, we do know that that the map extends holomorphically in a neighborhood of the Jove point. Since it is doubly parabolic, it is repelling, and this means that points in the boundary escape. So if we take cross-cut neighborhoods around this point, what we see is that points in the boundary should not stay in the cross-cut neighborhood too long. And this is telling us that if points in the boundary want to escape, that in this case many points in the boundary escape, they cannot do it through the dynamical axis, because if they do it through the dynamical axis, they would enter all these crosscuts, and this means that for the inner functions would be converging to the Dynamical point, and this cannot happen because the Dynamical point is repelling in the unit circle. So this is one example. The next example I wanted to show is also a doubly parabolic Baker domain, z plus 1 plus e to the minus z. This is a Fatus function, so very well-known Baker domain. But this now has infinite degree. the boundary of this Baker domain is a Cantor bouquet, so a collection of hairs together with their endpoints, and the situation is exactly the same. So points inside the Baker domain converge to infinity going to the right, and points in the curve, except for the endpoints, converge to infinity going to the left. So even though we have a lot of points escaping to the boundary, the points that escape to infinity going to the left, they are not doing the same as points inside the Baker domain. And this is why we don't see them if we look for the inner function. So here it's a little bit well explained, or more things at least. Again, for this function, we know for this Baker domain, we know explicitly the expression of the inner function, and we know that well, it's periodic, and the image of any of these intervals is everything, and this means that in particular there are points that, so the infinity, the Jove point is a singularity for this function, so it's no longer true the situation that we had before, that the Jove point repels on the both sides. It's no longer true because now it's a singularity, the Jove point, and actually there are points that escape to infinity. Well, it's easy to see from the graphic of the function that there should be points that escape to infinity, and this corresponds to hairs that the whole hair escape to infinity with imaginary part going to infinity. And these points are precisely the points in the Kara-Theodori set, because they are converging in the Kara-Theodori way to infinity. So this is the situation for doubly parabolic Baker domains. Maybe I write a little bit about this, but maybe it's okay. Well, I don't know. If you want to open the lab. So, for doubly parabolic Baker domains, recall that this means that for the Jove point, we have that it acts as a repelling point in the unit circle, and we know that almost every point doesn't converge to infinity. We have, so we can analyze the boundary in a more precise way, because we know that the set of points in the unit circle whose radial limit is infinity, this set of points are dense in the unit circle. So these situations that we have viewed, that there are a lot of accesses to infinity, because like here you can imagine that between all these curves there are accesses to infinity. So this is a general thing, and this in particular is telling us that if for any point in the unit circle we consider its cluster set, which is kind of the image of the point by the Riemann map, but taking into account that the image is discontinuous. So the set of points W we see such that there exists a sequence Zn G phi Zn goes to W. So this is the standard way, I would say, to look at images of a point by the Riemann map when the map is not continuous. So we take a point here, we consider any sequence that converges to this point, and then this point is in the cluster set. and the collection of, of all points that we can reach like this are the cluster set of the map. But so in some sense, the cluster set of a point is the part of the boundary that corresponds to this point under the Riemann map, more or less. But the good news, or the important idea here, is that having that accesses to infinity are dense in the boundary says that cluster set should be disjoint. So if we have 2 points in the unit circle, since accesses to infinity are dense, we can always find two points with radial limit infinity, and then when we apply the Riemann map, this means that the cluster set corresponding to this point should be here, and the cluster set corresponding to this point should be here. So the cluster sets are disjoint, and also these accesses to infinity that are dense help us keep track of what are doing the cluster sets with respect of what's doing chi for the inner function. So let me explain. So in some sense, Fn restricted to the cluster set of chi does the same as Gn of chi. Why? Because if we have, I don't know, a point and its orbit doing whatever, using this partition made by the accesses to infinity, we can know where the orbit of the cluster set is going. It should be doing exactly the same as the orbit of the point in the unit circle. So using these accesses to infinity, we can see in the dynamical plane what the orbit doing. And in particular, if our Jove point is here, using again accesses to infinity, we can know when a point is in the Campabadal set, because it should enter all these neighborhoods. So really, a point is in the Campabadal set. So X is in the Campabadal set. So it's converging to infinity, entering all these crosscut neighborhoods around the point, if and only if X is in the cluster set of some chi, and chi converges to infinity, to the Jove point. So really, these accesses to infinity allow us to say that a point is converging to P in the unit circle if the corresponding cluster set is doing the same in the dynamical plane. So if we come back to our first easy example, all these curves in the boundary are the cluster sets of different points. So any of these curves is the cluster set of a point in the unit circle. There are no points in the unit circle that converge to the Jove point. So when we look at the dynamical plane, we see that there are no points in the Campabadal set. And for the other example that we saw that now the Jove point is a singularity, and there are points that converge to infinity. Well, there are points in the real line converging to infinity. This corresponds in the dynamical plane of cluster sets of hairs. Each hair is a cluster set of a point doing the same, and for these points that are moving towards infinity, we see that the hair is also doing the same. Okay, this is what we can tell for double parabolic Baker domains. Let us see what happens for the other two two types of Baker domains. And as we will see, it's very different. So these are two examples of this is a hyperbolic Baker domain in the left, and here in the left is a simply parabolic Baker domain. What's the main difference? That here, well, in both cases, the boundary is a Jordan curve. This cannot happen for doubly parabolic Baker domains. Why? Because for doubly parabolic Baker domains, accesses to infinity are then. So we have a lot of accesses to infinity. If the boundary is a Jordan curve, we have one single access to infinity. So the situation is very different. And in fact, since the boundary is a Jordan curve, well, we have the same dynamics as it inside. So all points, here it is doubly parabolic, hyperbolic, with a fixed point in here, and all other points in the boundary converge to infinity. And here it is simply parabolic, so it's more or less a translation going up, and in the boundary we see also a translation going up, and all points converge to infinity. So here the whole boundary converges to infinity. But these Baker domains are very special because they are univalent. So one can ask, if they are not of degree 1, what happens? So let me show you an example. This is a hyperbolic Baker domain of infinite degree. And here we see a boundary which is much more similar to what we saw in the other example. So the boundary is also a Cantor bouquet. And in fact, if we look at the inner function, one thing that one should notice is that although the image is very similar as the image before, before we had very few points that escape to infinity going up and down because this has 0 measure. Here, almost every point is escaping to infinity, moving up or down, but there are plenty of other things happening. So this Baker domain, in fact, is the boundary is the Julia set. So in this boundary, we have periodic points, we have Bungee points, we have points with bounded orbit, we have several other things, and that we didn't have in the previous example. So I want you to make you that you realize that these boundaries that are kind of pathological because they are in the Julia set, but they have a very stable dynamics. Well, they are exceptions because they are univalent, but in a more general. So for all other Baker domains, even though if they are hyperbolic or simply parabolic, the dynamics are much more chaotic in the boundary. And well, now we have seen the examples. Let me write in the blackboard. So if you want to, yes, I will not need it more. So for hyperbolic and simply parabolic Baker domains, what we can deduce or think about the examples that we have seen. So the idea is that if they are univalent, this corresponds to, in some sense, to tame dynamics. But if it's not univalent, so if we have degree, then the dynamics are richer. And this is precisely what we observe for the inner function. So if the map is univalent, then G, the inner function, is a Möbius transformation. And since, well, it's hyperbolic or simply parabolic, we, in the upper half plane, this is a homothétie. Hyperbolic, or a translation. And what do we see in the unit circle? Well, now the unit circle is the real line. We see that there's a unique fixed point and all other points converge to the Jove point, or all points really converge to the Jove point. And this is what we saw in our examples. But if the map is not univalent, many other things happen. So when the situation is the same as when you iterate a polynomial, if the degree is 1, nothing happens. As long as the degree is 2, everything happens. We see exactly the same. So if the degree is greater than 2, we can consider the Fatou set of the inner function. So now the inner function, we consider the maximal extension. So so the Fatou set is the set of points for which there exists a neighborhood of this point, and iterates converge uniformly to the Jove point. So if our point is in the boundary or it's in the complement of the unities, we define G by reflection, and we can still define this. And there's the Julia set, which is the complement of the Fatou set. And now this set is non-empty and perfect. And in fact, it's the closure of the radially repelling fixed points. So now we cannot consider repelling fixed points in the usual sense because they may be in the unit circle, but we consider radial. As we have seen, considering radial limits is the good way of considering the images of points in the boundary, and also for points in the Julia set, we have that they are in the closure of accesses to infinity. So this idea that we had for doubly parabolic Baker domains, that the accesses to infinity help us to track the dynamics of the point and know that they are doing the same that they do for the inner functions, we still have it for points in the Julia set. And these things for the inner function, in some sense, they are telling us that we should expect richer dynamics in the boundary of Baker domains. Which is the kind of the problem, that it may happen that all these points that we see for the inner function are sent to infinity when applying the Riemann map. So it's not obvious that we should have richer dynamics in the boundary, but in some sense it's expectable. And this is our theorem. So if F is entire and U is non-univalent hyperbolic or simply parabolic Baker domain, and if we assume that there exists a point in the Julia set of the inner function and a crosscut neighborhood of this point T without singular points, the Campabadal set is non-empty. And apart from non-empty, it contains uncountably many accessible points. And if this is stronger in the following sense, so that the closure doesn't contain singular points, then there are infinitely many accessible periodic points and Banchi points in the boundary. And let me comment on the proof of the first one because it's really very easy. So as I said, the problem is that even though we have all these points doing crazy things for the inner function, we have to make sure that when we go to the dynamical plane, not all these points are sent to infinity. So a priori it may happen that although we have a set of points that are not converging to the Jove point, it may happen that all these points are sent to infinity. This set has zero measure, so a priori this may happen. But, well, it's known that, so if we show that the Julia set has a positive Hausdorff dimension, this is enough. Because this implies that has a positive logarithmic capacity and it's known that a Riemann map cannot send a set of positive logarithmic capacity to a single point. So not all points in the Julia set would be sent to infinity. And if we know that the singular set of F, so that there exists a crosscut without singular points, reflecting we have a disk in which we have all inverses well defined, and it's easy to see that we can find two contained pre-images, maybe of a larger period, but it doesn't matter. And with this easy iterated function system, one proves that the Julia set has positive Hausdorff dimension. So, proving the first part of the theorem. For the second part, once one has the same part, one can apply arguments similar that in the case of doubly parabolic Baker domains to prove the existence of periodic points. But I will not explain this today. So this is all what I wanted to say, and thank you for your attention.
Any questions, comments? I have a question, but I think Anna will hate me again. This huge part was that we know what's the behavior just from the measure theory, from the harmonic measure point of view, or from the Lebesgue measure point of view. So do we know that almost every point does something? So let's say we know that almost every point does whatever we like, and can we see something more about the remaining set? So we know that it's zero measure, but do we know it's of full dimension or of some small dimension? Do you know of any results? Or
I think that, that in general nothing is known.
Okay.
And in some, I erased the theorem you're referring to, but for hyperbolic and simply parabolic Baker domains, I think that until now that we studied this with Nuria, it wasn't known if there are points doing other things in the boundary. And concerning doubly parabolic Baker domains, I think that there are points which escape infinity have zero measure. I think that there are some partial results with me and Nuria, I don't know if anyone else studied this, saying that there are escaping points in the boundary, but the general question that if you have a Baker domain, is there a single escaping point in the boundary? I think this is an open question in general. And very difficult, I may say.
Thank you. Other questions, comments?
I think it would be good if you explain to those who are not familiar with dynamics of entire maps what you mean by bungee point.
A point which does not escape to infinity and also doesn't have a bounded orbit. So for polynomials, the points that escape to infinity are in the basin of infinity, and the remaining points have bounded orbit, so its orbit is in a compact set. But when you consider an entire function, there appear also these points that neither go to infinity nor stay bounded. And we can find them in these boundaries.
Okay, if there are no more questions, comments, let's thank Anna again.
Biscuits, the coffee.